Right. Hello, everyone. So we'll try to finish. We definitely have to finish the boundary layer discussion today. Next week, Chris will come back to finish her supersonic part, and that's it. That's the end of the module. So we started last week talking about boundary layers being a very, very important part of aerospace engineering, and it's all to do with the formation of a very thin layer on the basically usually on the millimeter scale, okay, but the influence of that in practical terms is quite significant. So I think we reached this stage last week, if I'm not wrong. So just to remind you that in terms of the total drag, of course we need to think about induced drag anyway, but we have two competing drag forces on an aircraft or an aircraft surface. We got the pressure drag and the skin friction drag. Now the pressure drag specifically to the pressure distribution, and basically what happens is if you try to keep the boundary layer attached without much flow separation, your pressure drag will go down. Otherwise it will go up. The skin friction drag is a little bit more complicated. It actually is a function of the type of boundary layer that you have, whether it's a laminar boundary layer or whether it's a turbulent boundary layer. So I have here some flow pictures and flow cases where you guys can kind of get a feel of the relative importance and contribution of those two types of drag. So flat plate perpendicular to the flow. So if you have a flat plate like this, flat plate is a very thin plate, extremely thin one, compared to the size of the plate itself. And if you just place that vertically to an incoming flow, what you will find is the whole flow actually separates at both ends, and you get a large wake with, as you guys can see, a lot of eddies behind it. So really it's completely separated flow, large wake, as I said, a lot of eddies. So in that case, your pressure drag contributes, well, it's basically almost the drag itself, the whole drag itself on the aircraft. The skin friction drag is only about 2% typically. Okay, so these cases here, you need to think about what can I do to reduce the pressure drag. Clearly the skin friction drag is very little, so there's no point spending energy trying to reduce that, but you really need to focus on pressure drag. Or at least you know there will be a lot of pressure drag. Now, of course, there are both kind of evils that you need to deal with, but it's important to know what type of drag you will be having, and therefore, in practical terms, what can you do to eliminate that part or to decrease it, because obviously the techniques we use for reducing one type of drag, whether pressure drag or skin friction drag, are not necessarily the same. There are various techniques for that, but it's important to know what you're dealing with. Kind of similar situation, not as bad, but well, almost the same. So if you have a cylinder like this, okay, and you have flow coming as well, particularly at high Reynolds numbers, then again you have the flow separates rather quickly and you get a thick wake and a lot of eddies as well. In this case, your pressure drag is large. So I think you guys are starting to see the picture. So whenever you see a lot of flow separation around any surface, like an airfoil or wing, you know your pressure drag is very high. Okay, so obviously one of the things you guys can tell me to stop that is, for example, delaying separation, or kind of make the flow, or what we call the flow reattachment. What can you do to make this flow reattach to the surface so that the pressure drag is reducing? So this is the kind of practical thinking you can do. So in terms of relative importance for the second case, the pressure drag could be up to 95% of the total drag, and skin friction is quite small. So now if we take the case of a thick airfoil, so what we mean by that is the thickness, or the maximum thickness, which is usually a percentage of the chord I would say anything after 10% of, or 10% maximum thickness, I would probably call that thick. 15 is definitely a thick airfoil. So in that case, if you guys think about it, we're not really, so it's a thick airfoil, it's kind of a bluff body, but it's not as bad as a cylinder. So we would expect the pressure drag to stay quite high of the total drag, but definitely not as bad as a circular cylinder. So with the thick airfoils, you get a lot of pressure drag because it is most likely you will have a lot of flow separation. Okay. The situation, so what do we have here? So I'm not sure if I consider this as a thick or is this meant as a thick or thin one, but let me just finish the discussion with the thin airfoil. The thin airfoil, what we call case D there, is kind of the almost the other way around. So the pressure drag now is reduced, so flow separation is much less likely, but the skin friction drag is actually increasing, which is annoying because at the end of the day as an engineer you've got a lot of drag anyway, but at least you know what type of drag you will get mostly. So and with a flat plate parallel to the flow, not at 90 degrees, so most of the drag will be skin friction drag and almost no pressure drag because very, very little flow separation will occur. Probably 0% here is quite exaggerated, to be honest. We should have put something, but mostly it will be skin friction drag. Now, of course, in aerospace applications, you probably will be thinking about these two types, thick airfoils, thin airfoils, probably much more on thin airfoils because most of flight these days, high-speed flight, they use thin airfoils. So in that case, you immediately see that the skin friction is actually quite a high proportion. And of course, skin friction comes from the boundary layer. This is why we're studying the boundary layer. Now, however, to make our life easier, what we're going to do, actually for practical calculations, we're going to make an assumption. It's an assumption with engineers, but we're going to assume that all surfaces actually approximate to a flat plate, which is parallel to the flow. So instead of thinking of having a wing with a certain thickness, we're going to ignore that thickness and just treat the wing as a flat plate. So that's all nice and well, but you know that calculation you're making of the skin friction drag is only an approximation. Okay, you're basing it on a flat plate, not the real airfoil. You have to, in real life, you have to add some adjustments or corrections to make your drag calculations correct. But to a first approximation is actually not a bad approximation to make. Okay, and this is what we're going to do. So keep that in mind. So we're going to base all our calculations on the assumption of a flat plate, not a real airfoil. Okay. So I'm not going to talk about these again, probably just some of the key points. Skin friction drag can account for about half or more of the drag force on an aircraft, like an A380. So when you guys think about it, if you just reduce the drag by a few percent, even 1 or 2%, that actually, in terms of savings, that counts to huge amounts of money. Now, I'm always wary when I read research papers and some clearly people who do not appreciate how hard it is to reduce the drag. They say, oh, I designed this new wing and it gives me, I don't know, 20%. No, we designed this aircraft and it gives us 20% reduction in drag. I'm pretty sure that's not true because it's really, really difficult to get that amount. People, I would usually believe a very few percent usually because that's how it is really. It's not easy. It's a very, very difficult problem to reduce the drag. So anyone who says give you like a huge reduction in drag with a new design, don't believe that. If you actually look in the numbers, I'm sure you'll find there's something wrong somewhere. Now, of more importance to us in terms of boundary layers is that the friction drag, if you have a turbulent boundary layer, the skin friction drag is actually higher than in a laminar boundary layer. So from a practical point of view, we want our aircraft wings to have a laminar flow rather than a turbulent flow. There is a catch to that, however, because what we will find is that, okay, you can have a laminar boundary layer on your wings. The problem is the smallest of disturbance to that laminar boundary layer will make it either separate or transition to turbulent boundary layer anyway, which gives you more skin friction drag. Now, if the laminar boundary layer separates more easily, you will get a lot of flow separation, and therefore your pressure drag increases. Or if it transitions to turbulent boundary layer, then your skin friction go up anyway. So, and this is actually a real headache for all aircraft manufacturers or for people who try and reduce the drag. It's kind of, well, which type of boundary layer shall we aim for? And whatever you do, you're always losing one way or the other. So, but at least in terms of skin friction drag, we know you want the laminar, or you want the boundary layer to remain laminar as much as possible. Okay, so, well, that's just discussion of what I said. What are the advantages and disadvantages of turbulent flow? So, a turbulent flow compared with laminar flow, in terms of disadvantages, I told you already it has a higher skin friction and therefore a higher skin friction drag. So that's not good. However, the good thing about a turbulent boundary layer is that it can remain attached on the surface much better than the laminar one, and therefore the possibility of having high pressure drag is hugely reduced. But then you have high skin friction drag, so it's kind of, it's very difficult. So also one thing about turbulent flows is they're very good with mixing. So in situations where you want a lot, this is really to do with heat transfer maybe and mixing flow problems, but they're very good at mixing. So any flow situation like, I don't know, flow in an engine where you want things to be well mixed, you really want a turbulent flow, not a laminar one, because with turbulence you get a lot of mixing, and that's very good for the quality of the flow you have in the engine, for example. But at least from an aerodynamic point of view, I hope you guys can see kind of the eternal struggle for aerospace engineering between pressure drag on one side and the skin friction drag on the other. So let me just give you, so this flow picture here is meant to represent flow around kind of a circular cylinder, and it's kind of showing you how if you have a laminar boundary layer which is on the top compared to a turbulent boundary layer which is the bottom. Now the blue circle is the approximate location of where the separation occurs. Now, I told you that turbulent boundary layer is able to keep the boundary layer attached over a longer surface, and therefore it doesn't separate early, so the pressure drag is reduced. So here we have a laminar boundary layer, the flow separates there, so you get flow separation earlier. Here, hopefully guys you can see, the boundary layer remains attached much longer distance, and it only starts separating much further at the back. So in this case, we know, between the two cases, that this has a high pressure drag, this has a low pressure drag, but more likely this has a high skin friction drag anyway, compared to this. So it's kind of what's the best thing? And to be honest, it's very difficult to say what's the best answer. I would say, depending on the flight. Now, in cruise, it turns out that skin friction drag is really the one that we target because it's quite high. So we try to make the boundary layer as laminar as possible. But in other situations, it may not be the case. So just very briefly, I'll give you some qualitative things about transition to turbulence. So there are many things that can cause transition to turbulence. One of which is the roughness on the surface. So if you have a wing which is very smooth and a wing which is rough, then the transition is different between a rough and a smooth surface. And we can actually, in fact, we can look at this from a golf ball. Anyone plays golf here? My God, no one plays golf? You guys are not in a golf club? What's going on? There must be someone in a golf club, come on. You played golf? Mini golf. Oh, mini golf. Okay. Honestly, I don't play golf as well, so that's fine. Anyway, so you might be interested to know why kind of high quality golf balls nowadays, they have what we call these dimples on their surface. And the reason for that is they make the boundary layer turbulent. So they actually promote transition to turbulence. And that turbulence will make the boundary layer remain attached over the ball most of the time. It's only really towards the back that you get little flow separation. Meaning there is very little, or not very little, but the pressure drag is reduced. So for a golf player, that means more accuracy towards your target, and you can also make it fly further if you need to. So this is actually, it's interesting how golf ball designers, they got inspiration from aerodynamics, and this is a real case. This is not fiction. So next time you play golf, you look at the ball, most likely it has dimples on it. That's the reason. Okay, so now this is for a golf ball. However, I've just told you that for a real aircraft wing, the fact that you have a turbulent boundary layer is not necessarily a good news, because you have high skin friction drag. One of the things that can cause the wing of the aircraft to become suddenly rough is things like dirt. This is why they clean aircraft all the time. Insect hits, believe it or not, that could be a problem. Manufacturing irregularities, sorry. So this is basically not ensuring that the surface is well finished. So very little things on the surface can cause skin friction drag. So you're promoting turbulent boundary layer, i.e. you are causing a high skin friction drag. And all of these things are very important in aerospace. So I'm sure you get engineers around airliners who make sure we don't get these problems, or dirt, okay? And of course, to keep your customers happy, of course, I'm sure all manufacturers of aircraft make their manufacturing as best as possible without these irregularities. Right. So now, just as an example of promoting transition to turbulent boundary layer, which on one hand increases the skin friction drag but reduces the pressure drag, we have the NASA's X-33 experimental body. So whenever you see this X, it means experimental. And they have that, of course, they have money, they have critical mass of very clever people, and they can do whatever they like, really. So the X-33 is actually a bluff body. So bluff body means there is possibility of flow separation and high pressure drag. So clearly, they need to do something about it to reduce the pressure drag. So the concern here is not the skin friction, but the pressure drag. So what you guys can do, or what they did, they actually made the surface on one side of the body rough, and they also used vortex generators. If you guys remember last week, we said that vortex generators, they energize the boundary layer, so they work as if it was a turbulent boundary layer, and they actually made the boundary layer more resistant to separation, which actually reduced the pressure drag on the body. Here's an artist's impression of the X-33. You can read more about it. This is clearly a bluff body, which is prone to a lot of flow separation, i.e. a lot of pressure drag. So it makes sense to use things like roughening the surface on purpose, or using vortex generators that create a more turbulent boundary layer, which is more resistant to flow separation, okay? But they will probably come back and tell you, okay, that's fine and good, but actually in doing so, you're also increasing the skin friction drag. So, but the hope is, by combining and thinking about both pressure drag and skin friction drag, you get to kind of a sweet spot where the overall drag hopefully is reduced, okay? So that's one way of transitioning to turbulent boundary layer, is through basically irregularities and surface roughness and the rest of it. Surface temperature, if you have, in a more general case, is actually inside the boundary layer because of skin friction drag and the flow particles rubbing against each other a lot, that creates actually heat. So actually in a general case, actually inside the boundary layer, if you were to measure the temperature of the boundary layer compared to the outside flow, you'll actually find it's hotter inside the boundary layer. Now that heat and a lot of eddies because of what's happening inside the boundary layer, all these things, they can actually promote transition to turbulence. So the fact that the boundary layer is hot kind of on its own naturally will lead to instabilities that will then transition the boundary layer to being turbulent. Okay, one of the things is what we call adverse pressure gradients. You probably, if you ever read some books, you might come across what is adverse pressure gradients. Basically, here is how you think about adverse pressure gradient. If you were kind of think of yourself as a small particle going from leading edge to the trailing edge, and you're kind of measuring the pressure as you go along the surface. If you find yourself, as you're going from leading edge to the trailing edge, you get kind of, you're being slowed down by, as if it's someone is pushing you back. That's what adverse pressure gradients is. So if you go from leading edge to the trailing edge and you find that the pressure at some point starts to push you back and it's increasing, that's what adverse pressure gradients are. So these adverse pressure gradients, they can cause flow separation. So that's one thing. That's actually one of the key reasons why the boundary layer separates, because the boundary layer tries to grow over the body surface, but because of pressure gradients pushing the opposite direction, at some point they push the boundary layer to separate. But also, they can cause transition to turbulence as well. Now, the opposite to adverse pressure gradients is obviously favorable pressure gradients. And that means as you go from leading edge to the trailing edge, you'll just find that the pressure is continuously decreasing rather than at some point you find it is increasing and trying to stop you. So, and of course, with favorable pressure gradients, as you'd imagine, this is actually very good to preserve laminar flow, because adverse pressure gradients, they encourage turbulence and separation. So I don't want to dwell, just to give you some ideas. Increased free stream turbulence. Well, free stream turbulence, this is actually quite important in wind tunnel testing. I'm sure, have you guys, some of you who, obviously you've submitted your CFD now, in your experimental data, did you come across people talking about free stream turbulence or turbulence level? Anyone? Surely. No, okay. Did you read your experimental reports? Yes, you come across?
Yeah, we use 5% for ours to match.
Very good, yeah, that's exactly what we did, yeah? But they express it as what we call turbulence intensity, but that's exactly the same. So, different levels of turbulence coming and interacting with your aircraft or your wing will have different effects on the transition to turbulence. So, in a very simple sense, the higher the level of the free stream turbulence, the higher the possibility your boundary layer will be turbulent. Likewise, if you increase the Mach number, i.e. if you fly faster, it is much likely that your boundary layer will become turbulent, okay? And finally, in terms of the curvature of the surface, you have, if it's, I always get confused with this, if it's concave, which is bulging inwards, that encourages turbulence. Otherwise, if it's convex surface, which is bulging outwards, it actually stabilizes the boundary layer and reduce its tendency to go to turbulent. So these are just kind of things maybe later on, I don't know, if you're doing some aerodynamic things, that you try to remember these effects on the transition to turbulent boundary layer. So in summary, let's just kind of summarize for you the main characteristics between laminar and turbulent boundary layers. And I think some of these are quite important to remember, kind of as an aerospace engineer at least. You straight away, you know, if you have a laminar boundary layer, you have low skin friction drag. Otherwise, is high skin friction drag with turbulent boundary layer. I always like to give the example, you go to an interview, and they can actually catch you with a simple question like that, honestly. They say, well, why is turbulent boundary layer, they actually probably ask you, is turbulent boundary layer better or laminar? It's just a tricky question. It's not a straight answer. You can say, it depends what you're talking about. You say, if you want to reduce the skin friction drag, you want laminar boundary layer. If you want to reduce the pressure drag, you want a turbulent boundary layer. And that's the perfect answer. So don't ever say, oh, it's turbulent, without giving, or whatever, without giving an answer. So laminar, of course, we know it's a smooth flow, but it has little mixing. Okay, that's the probably key thing there. So if you are in situations where you, as I said, you want a lot of mixing in the flow for whatever reason, then you really don't want a laminar flow, you want a turbulent flow. So turbulent flow can actually be quite important. If you think about your teacup, if you make your tea, probably coffee is better. You put the coffee, obviously, if you don't stir it, sorry, thanks. If you don't stirring it, you're actually making the flow turbulent. And that actually increases the mixing. And that makes the coffee mixes more with hot water, and you get the coffee much quicker. Whereas if you don't do that, then, yeah. Right, it thickens slowly. We will see this actually. So we will see that the thickness of the boundary layer is a lot less in laminar compared to turbulent. The problem with laminar, if you have a high Reynolds number, it can go straight away to turbulent. And finally, yes, if you have adverse pressure gradients, remember this word, adverse pressure gradients along the surface. If the boundary layer is laminar, unfortunately, the adverse pressure gradients will have a much greater effect on a laminar boundary layer compared with a turbulent one. So they can make the laminar boundary layer transition to turbulence, or they can cause the boundary layer, the laminar boundary layer, to separate. Either of which, one of them is bad for skin friction, the other is bad for pressure drag. So it's really difficult to say which one is better as a general rule, but I would say depending on your application, depending what's the relative importance of each type of drag, then you will target which type of boundary layer you really want. Okay, so let's talk about kind of some of the parameters we usually use as engineers in aerospace to kind of describe the boundary layers. The first one, it's the boundary layer thickness. It's basically how thick or what's the height of the boundary layer as it grows along the surface of a wing, for example. We usually define that we're using the simple delta. So the height of the boundary delta is the thickness of the boundary layer, or the height of it from the surface, when the speed, the local speed u, is 99% of the free stream speed. That's what it means. So wherever the local speed little u is 99% of u infinity, or almost u infinity, then that defines the boundary layer thickness. So it's basically the thickness, all right? Number two is the displacement thickness. Now, probably one way to try to understand displacement thickness is the following. So what I have here is two situations. The first one, this is the flow with no boundary layer. So we just imagine there is a flow going over the surface, but there is no boundary layer, which is basically the inviscid flow, isn't it? So, so the free stream speed is u infinity. And now we compare this situation. Now in this case, of course, what you guys notice very quickly is that clearly, because there is no boundary layer, there is no change in speed. The speed is all the same everywhere, right? And it's u infinity. Now once you have a surface and you create a boundary layer which changes from, of course, zero velocity, the no slip condition at the wall, to u infinity at some height delta, what the boundary layer does, because it's actually physically sitting there, what it does, if you guys think about it, is kind of, because of this layer itself, it kind of pushes these streamlines, if they were inviscid, they kind of pushes them up, yeah? It kind of displays those streamlines. So this is what the concept of displacement thickness is. So it's basically how much the streamlines would have been displaced if the flow was inviscid due to the presence of the boundary layer. So this is one way of thinking about it. So that's the displacement thickness is defined as delta star. And it's just the integral. I know it's from 0 to infinity, but let me just delta, because we really stop at delta anyway. Right, so what is the delete? That's not necessarily a wrong definition, but delta, it's fine. Okay, so it's the integral from 0 to the edge of the boundary layer of 1 minus u over u infinity. Again, I should have put u infinity there. Sorry, guys. It should be u infinity. But anyway, capital U is the free stream speed. So u over u infinity, actually this defines your profile in the boundary layer. And if you take the integral of 1 minus that profile along the y direction, then that will give you the displacement thickness. The next one is momentum thickness, symbol theta. This is really to do, again, it's to do with displacing the streamlines of an inviscid flow, but due to the fact that the presence of the boundary layer leads to a reduction in the momentum that passes through a section. And that could be expressed as a displacement due to the momentum, and that's why it's called momentum deficit, that's why it's called momentum thickness. So this one is actually to do with reduction of the mass flow rate. This one to do with the reduction or deficit in momentum. But they're really both, they're kind of slightly different ways of telling you that the boundary layer will displace the streamlines, okay? And they're both displacement thicknesses. So delta star and theta. The energy is very similar. So let me just, if you guys look very carefully how delta star and theta are related. So delta star is this integral. To get theta, you just multiply the whole thing by u over u infinity. Okay, and with the energy, energy thickness is now, the only difference between theta and delta double star is the u over capital U is squared. Okay. And again, it's to do with displacing the streamlines due to the reduction in kinetic energy that is caused by the presence of the boundary layer. All right. So, in summary, we got the boundary layer thickness delta. This is where local speed u is 99% of free stream speed. Displacement thickness is to do with the displacing the streamlines due to the boundary layer and is related to reduction in mass flow rate because of the boundary layer. Momentum thickness, displacement of streamlines due to the reduction in momentum through the boundary layer. And finally, again, another displacement, energy displacement thickness due to the reduction in kinetic energy in the boundary layer. Because as you guys remember, we have the boundary layer, the speed goes to 0 at the surface, and then it grows. Okay, but compared to an inviscid flow, the speed would have been u infinity. It will never be 0 at the surface. So that's why there is a reduction in kinetic energy due to the boundary layer. And we express that as a thickness, kinetic energy thickness. In practice, the most important ones are the first three, really, delta star, and theta. And in the example sheet, I think there are a couple of questions where we actually calculate these guys. But kinetic energy thickness, probably I won't bother you with that, but it's just another measure of displacements of streamlines. Now, in terms of typical, kind of how do they relate to each other, or how do they look typically? Now, first of all, if we have a surface, like a flat plate or a wing, and the flow is coming left to right, and then what we find is that the boundary layer grows over the surface from the leading edge to the trailing edge. So, and it's not constant. So the blue line shows you what the thickness is. And you guys can see at the leading edge is 0, and then it grows and becomes fatter and fatter, or bigger and bigger. It's not nice to see fatter and fatter, isn't it? But sorry, it's just bigger and bigger. So, and that's the thickness delta. So clearly, the boundary layer becomes more as we go along the surface. Now, in terms of delta star and theta, they follow the same trend. So as delta becomes bigger, delta star and theta becomes bigger. But you guys can see very clearly their relative size. So delta is the biggest one, followed by delta star, and followed by theta. Okay, so it's quite useful, again, to remember those things in practical terms. For example, I don't know, if you're given an example to work out displacement thickness and momentum thickness, if you end up with momentum thickness greater than your displacement thickness, you've done something wrong, right? So that helps to keep you kind of aware that delta is greater than delta star, and delta star is greater than delta. Okay. So this is for kind of keep you in order, if you like.